Hi everyone, welcome to the next video. This is a continuation of the last one where we are actually discussing about shell coding. In today's video, I'm gonna actually show you how to get till a WinExec function. Uh, WinExec function, if you don't know, is the function that you can use to run maybe Notepad, Brave, a calculator, or any application that you want. So in last video, we reached till the base address of kernel 32 DLL. So I'm starting from there. In this video, I'm going to actually cover a new tool called the PE viewer, and in the last video I just showcased X32DBG as well for debugging. So I'll be covering more of that during this video as well. So first things first, we have reached till the base address of kernel 32, and if I compile and I run this, just going to showcase that we are reaching till there. So you can see the in EAX you are pointing to the base address of kernel 32. So that's where we stopped last time. So now we are going to work on the next set of things, that is to reach till the particular function inside the kernel 32 DLL. Here I'm going to introduce a new tool called a PE viewer. So PE view actually allows you to view what's inside the DLLs, the structure of it, what all are in the headers, and other details like that. It's a great way to understand structure of a DLL. Um, that's at the very base level. You use this for a lot more other things. Specifically in our case for writing the shellcode, we'll be using this to find the WinExec function, and also this particular tool will be helping us to know where to reach, and specifically there are multiple sections that we need to cover in order to reach till that function. This particular tool is going to help us with that. This is just a normal tool. If I close everything, it will just look like this, and if I open and I'm going into Windows System 32 and I'm checking for the kernel 32 DLL, and I have imported that right now. So now we are at the base address of the kernel 32 DLL as per the X32 DBG. We have seen that. So what does that mean? So we are literally right here at the start of the program, and there are a lot of things in the DLL that we need to check out. Before going forward, we need to discuss a bit about the kernel 32 DLL. Kernel 32 DLL contains a lot of things. It contains many headers like the image file header, optional headers, um, and if you go into the export address table, which contains a list of many functions that are there in the kernel 32 DLL. Uh, Kernel 32 DLL actually handles a lot of things like file operations, process information, thread informations, synchronizations, then system information. So it has a lot of functions to actually, uh, you know, it has a lot of functions which defines all of these functionalities. But specifically in our case, we'll be looking at a function called WinExec, which resides right here. LMNOPQRSTUVW, that is WinExec. So this is the particular function that we want to invoke. And now, as you can see, I am in a in a structure, uh, and the inside of that, I'm specifically at an array called name pointer table. Um, So I'm actually looking at the entirety of name pointer table with values, which contains a lot of these function names. So the name pointer table actually contains the name of these functions, and it is actually pointing to all of these function names. And the second thing that we want to look at will be the address table, which actually points to the address of these tables. So here also you can find all of the things that are present there. Your VNX is also there. So this is actually pointing to the virtual address of WinExec, and the name pointer table is actually pointing to the name of these functions. So right now, as you know, we are at the beginning of the kernel 32 DLL, but during this section we are going to actually traverse through this thing and reach till the export name pointer table and loop through this entire thing to find WinExec. And once we find the WinExec, we are going to find the functions virtual address as well. So that is our aim during this video, to find the WinExec function and find its memory address. Great. Now let's actually get started. Now from kernel 32 DLL, the first thing that we need to do is to reach till the headers. Headers is the one that defines where everything are. So in the DOS header, you can find the first offset to the new exe header, that is at 3C. So this will actually be pointing to the NT header that is here. NT header is a structure. So there are a lot of details that I'll be covering during this video. So maybe you can note these things down, but let's write it as we go. First thing we need to go is we need to move um, EAX to EAX plus 0x3C. That will uh, yeah, so I think that will get us to the offset to the new XA header, which means we are actually at the NT headers. All right, perfect. Now you might ask, why are we even here, and what's the need for going till the uh, NT header actually? So right now I have some of the P formats, image optional header, yeah, image and NT header x32 structure. So this is the image NT. So it's a structure. It's in a C++ form. It's a structure right here. So you have the signature, the file header, and the optional header. As you can see in the same P view, you can see signature, image file header, and optional header. Um, okay, so the reason why we need to go to the NT header is to actually go to the optional header. So the optional header is actually there inside the NT header. Why do we want to go to the optional header is your next question. It's in the optional header you actually have uh, so the optional header is also a structure. This is how the structure looks like. So these are all individual values or variables that are there, and all of these export table, import table are arrays. So we need to go to the export table array, which contains the export address table and the export name pointer table. So first we are here right now. Now we need to traverse the file header till we reach the optional header, and inside the optional header we need to traverse till the export table. From export table we need to actually find the address table and the name pointer table. I know it sounds very complicated, but we can simplify this. Okay, perfect. So as you see, we need to actually calculate the sizes of these structures as well. The image NT header, you can see it contains all of these things like the machine, the number of sections, timestamp. You can just go here. It has all these same things. But why I am here is that I want to know the size of the structure, so that I need to find the particular address where the optional header starts. So I will be adding a lot of things. So I have my very handy calculator right here to calculate a lot of things. So let's start with the first level of calculation. That is from the image NT header I need to reach to the optional header. So signature is um, as per here you can see signature is of a size 4 byte, and we don't know what the image file header contains. I know size of the image file, so we are going to calculate it. So we are going to add 4 first because signature is of size 4, and machine is the first value variable that is there, that is of a word size. Word size is 2, dword is 4. We'll be mostly seeing word and dwords here, so we'll just adding that. So how many words are there? There are 2 words, machine and number of sections, so that is equal to 4. Then I'll add there are 3 dwords, so that will total to 12. Then there are 2 words again, so that is 2 plus 2 4, so that is 24. So now we have reached, I guess, the end of the image file header. So if you go back to the P viewer, we reached till image file header. Now the optional header starts. So now we have 24 here. So now we are right at the start of the optional header. Now we need to calculate optional header till here. So we need to do a lot of calculation again. Perfect. So we'll just go to image of file header. Where is the optional header? Structure 32. Phew, okay, that's a lot. So if you can see it, I'll focus it again. So we need to calculate all of these again. So we added till the byte, that's 28. Now let's add the rest of the things. That is, there are 4 D words, 1, 2, 3, 4. Excuse me, it's not 4. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 D words. So 9 into 4. So that's 36. And after that there is 1, 2, 3, 4, 5, 6 words. That is 12. So then how many other D words are there? 1, 2, 3, 4 more D words. 4 D words. 5, 6, 7, 8, 9, 10 D words. So that is adding a total to 40. And 2 words. So that is 4. So if I'm gonna put the 120, right? So if I'm gonna just add the 120 into hex, I have a hex calculator right here, and that is 78. So that is how many bytes there are. So converting that to hex is 78. So let's move back to our assembler. Okay, so now we found 78 that is present. There's one step that we didn't do here. So we added the EAX to EAX0, X3, uh, that is the offset to the NT header, but we didn't actually compute that. So we already have the base address of what to say, kernel 32 DLL and ESI. Next thing to do is actually calculate the load effective address of the same thing. So load effective address basically means you are just computing it's an arithmetic operation of these addresses. So you are just computing the address without accessing it. So that is basically what it means. So we want the load effective address of EAX plus ESI. So ESI contains the base address of kernel 32, and you now added the offset to the NT headers. That's added. Now EAX will contain the particular address to the NT header. Now we'll do the same with the 0x78 that we found, which if you look at the P viewer right here, there is a lot of things here. We will reach till the export table. So that is 0x78. So we're going to do the same thing. We are going to move EAX and EAX plus 0x78. Once we add that, we're going to do again a load effective address on EAX, that is EAX plus ESI. Perfect. Now we are actually at the export table, that is here. Now what is that meaning? So the export table means we are at the export directory. So this is another structure with all of these information. In this structure we need to reach till the address table and the name pointer table. We need to store the value of the address table in one register and the name pointer table in another register. So that's the next thing to do. Now the question is, we need to again find the image export directory. Is this correct? Yeah, image export directory is this one, and in that we have characteristics, timestamp, major version, minor version. So this is 32 bits and this is 16 bits. So let's count how many 32 bits there are. There is like 1 2 3 4 5 6, and the next one is the address of function, and the one after that is the address of name. So we need both of these things. So we'll calculate till here and store it in two different registers. So that is, this is 1 2 3 4 5 and 6 and 7. 1 2 3 1 2 3 4 5 6. That is 6 was a 24 plus 24 plus 4, that is 30. So if you do hex of 30 and you convert it, you get wait, am I wrong here? I think I'm wrong here. 1 second. My calculation was wrong. 1 2 3 4 5 6 6 3 4 5 and 6. 6 4 is 24. 24 plus 4 is 28, right? It should have been 28. Convert. Yeah, perfect. So 1C points to the address table, which contains address of functions. And what is the name pointer table? So we just need to calculate till name pointer table as well. So name pointer table is another addition of 4. So if I add another 4 to this, that is, it becomes 32 and 20. So we need to go to the offsets of 1C and 20. Perfect. So now that is known. Let's do this. Let's store the value into another register and do the next set of computation. So we'll do move EBX, which will have EAX plus 0x1C. So no, we'll do that. We'll store the address to EAX. So load effective address of EAX will be EAX plus ESI. Perfect. And then we'll do EBX. EBX will have what? EBX will have EAX, not EAX. Oh, I did something wrong here, because now it will have a different value, right? Oh, okay. So ideally I should have done move EBX to EAX plus 0x1C, and load effective address of EBX should be EBX plus ESI. Okay, so that means EBX will have the address to the name pointer. Instead of 1C, it should be 20, and EAX will have the address to the functions. Now it is better. Yeah, this is much better. Phew. Okay, I know there's a lot of complications. So we are now having both the values of name pointer table and the address table. So name pointer table will contain all of these names. Now we need to write a loop to traverse it, and before that we just need to do another thing, that is, we need to sort ECX, because ECX is what I'm using for a counter, and I'm going to move EDI with a value of WinExec, that is win E, because it's only a 4. So how I'm going to search through this array is using, if we can find a certain pattern in the functions, then we will take it. So we don't want to actually search the entire WinExec. If we can search for just WinE, right, we will be able to find the functions basically. So that's the idea here. So if I go to write WinExec, it's here. So there's nothing quite like WinExec here. This is the only one with WinE right here. We are seeing all the functions with the name W here. So if you can just see WINE, something that starts with WINE, then we know it's WinExec. So WINE, and WINE should be in little-endian, so it should look like ENIW when I'm entering in the value. So I have an ASCII table right here to see the values. So we'll start with capital E. Capital E will be 45. 045. Then it's small n is 6e. Then after n it's I, that is 69. Then after I, w n e n i w, right? It's capital W after that. It's capital W is 57. So we have 4 bytes of values here. So I think we are good to go here. The ECX will be our looping the counter, which will be counting, which will be using as the counter for each function. We'll find each function name. We'll check if it is WinExec. If it is not, we will keep incrementing ECX. So that's what's going to happen here. All right. Okay, now what we need to do is, first part is we need to move EDX to, so the name pointer table is at EBX. So we need to do that with move EBX plus ECX star 4, because each of that is a 4 byte value that we are checking at. So that's why we are using a 4 here. Okay, perfect. And the next thing to do is that we need to find the load effective address of EDX. That will be EDX plus ESI. Now we actually are looking at the particular name. Now we are going to increment ECX so that whatever happens. Next thing to do is just a comparison. So comparison will be, we are actually looking at EDI and the value inside of EDX. And if it's not equal to, then we will ask it to jump to JN1 or the L1, sorry, L1. And if it is true, right, then what do we need to do? We now have the particular name pointing to the WinExec. Now we will move EAX to that. That is EAX. We'll do EAX is actually pointing to the address function, address of functions. So we will have EAX in addition with ESI, not ESI, ECX multiplied by 4. Am I correct? Yes. So next thing to do is load effective address of EAX will be pointed by EAX plus ESI. We are adding the base address with the value at EAX. So now we are actually at the function. That's it. I think we have reached. We just need to run it once and to see if everything is working fine. Just need to check if, yeah, perfect. I'll just compile this. Compilation is successful and I'll run it here. and I'll just show you what's happening. Once we start, we have exported. Just look at the registers that are here. This will give you a good reference. So we have reached till ECX where we are storing it. We have the WinExec inside that. We are doing the first loop. You see the acquire SR lock exclusive, and that is being compared to the value at EDI. And we're just going to go like that. New functions, you can see activate ATCTX. That is another function. We just run it till here. See, you can see we have EDX in the name of EDX in EDX. Sorry, name of WinExec in EDX, and actually the address of the function WinExec in kernel 32 in EAX. So now we have actually reached till WinExec. So that's all for this video. Next video I'll be actually running uh, an application using WinExec, and then we will move into the further part of extracting the shellcode from this application. I hope you liked it. This is a long video. It contains a lot of details. I'll add all the links. You can go through this video a few times to understand all of it and maybe write this on your own as well. Thank you so much for watching.